in the last lecture, we'll learn some basics about C++ because we need to use C++ for the remaining programming practice. So the system to be used for this course is ThreadMentor. ThreadMentor consists of a class library and a visualization system. The class library provides all the mechanisms for thread management and synchronization primitives. The visualization system helps you visualize the dynamic behavior of multi-threaded program. The development of ThreadMentor was supported by the National Science Foundation for 3 years. So the design of ThreadMentor, as I mentioned, is basically helping you see the internal execution behavior of your threaded program. So the architecture of ThreadMentor is a class library and a visualization system. So let's talk about the class library. Your program is here on the top level, and that is your C++ program. And then when you need any synchronization stuff, for example, you have to pause the execution of a thread due to whatever reason until something or an event will happen sometime later. So you need synchronization. Under the layer of synchronization, you will see thread kernels. This thread kernel supports, say, thread creation, thread join, thread management, and so on. So the lowest layer consists of the system part of thread support. And this system was designed more than 2 decades ago. So it supports Windows 32 and Sun Computer's Solaris system, pthread, and a thread kernel designed by a group of wonderful graduate students of this department. We refer it to MTU thread. So today, the department has no Solaris machine, and Windows moved to Windows 64. So these two are no more needed. And this MTU thread kernel is no more supported. So today, we only use pthread. So when your program is going to do a synchronization, and the synchronization may cause your executing thread to wait or to resume and something, they go down to the thread kernel. The thread kernel, on the other hand, will call the pthread system for further support. So this is your program. You only write this part. The synchronization thread kernels are part of the ThreadMentor class library. pthread is available under every Linux and Unix system. So this is your part. The visualization system of ThreadMentor is not written by you. And actually, you are not able to call anything in the visualization system. The visualization system runs in a separate address space as a different process. So when your program starts to run, your program, due to the mechanism implicitly built into ThreadMentor, the visualization system will be brought up running in a different process. So when there is any synchronization activity or thread management activity happening in your program, the ThreadMentor class library communicates with the visualization system. So here, as I said, any activity related to synchronization and any activity related to thread management, we only take care of these two. Any activity that happens in here or here will be informed or sent to the visualization system. The visualization system got the message from either the synchronization or the thread kernel. The visualization system will show the corresponding activity on screen in a visual way. So why do we design visualization to run in a separate address space? The reason is very simple. For a beginner, your program initially would be rather buggy. And what if your program crashed due to a reason in your program? Now, if the visualization is part of your, is compiled to become part of your program, you could blame the visualization rather than your program. So it's human nature. So in order to isolate your problem and the visualization's problem, the visualization is run in a separate address space. So your program only communicates with the visualization through some kind of a message passing. As long as the message is correct, the visualization system is able to show you the corresponding activity in a visual way. Unless you are able to corrupt the messages to be sent to the visualization system, it's unlikely your program will crash the visualization system. And that is why this system is written in a class library for you to use in your address space. And the visualization system is run in a separate address space. This system has been used for more than 2 decades. Initially, as a testing vehicle for that National Science Foundation project. Through that testing and pilot using, we published a whole lot of papers about it to promote multi-threaded computing near the end of 20th century. And then we use it in an operating system course for about a decade. And now we can use it in this course. Why we design ThreadMentor in this way rather than just using Java or C++? Well, the reason is very simple. ThreadMentor follows the very, very simple and very intuitive statement structure without asking to do a whole lot of things, like we will be talking about with a pthread and a job, and we will also mention Java. So this is a way to minimize your effort in terms of writing programs by focusing on the syntax and the semantics. Instead, we provide you with a very simple platform so that whatever the class slides will say, you just directly used in your C++ program under ThreadMentor. So in this lecture, we will discuss a very simple example telling you how easy it is for you to write a multi-threaded program. And even just for you to write a quicksort program quite easily. We mentioned how to write a Quicksort multi-threaded version when we discussed the thread components. So basic thread management under ThreadMentor consists of thread creation, just like a fork for you to create a process. Thread termination is similar to exit system call. Thread join, you guess, it's going to be the system call wait. And then actually ThreadMentor provides something even more. Remember, we talk about yield at the end of the thread components. Yield is used for cooperative scheduling among fibers. But ThreadMentor supports thread yield. And furthermore, ThreadMentor also supports suspend and resume. This is something we talk about at the end of the second lecture of the general information components as part of the kill command. Remember, we talk about sick kill, sick int, which is for control C. We also mentioned in passing, you could use sick stop to stop the execution or suspend the execution of a process. And you could use sick count, C-O-N-T, to continue the execution of a stopped process. So suspend corresponds to suspending the execution of your thread. Resume is similar to sick count to resume the execution of a suspended thread. However, in this course, we are not going to use thread yield and the thread suspend resume because in our experience, the use of thread suspend and resume can be very risky because you can easily generate deadlock. And thread yield is implemented in a slightly different way. We will mention that a few slides later. So basically, we disable the suspend resume capability under ThreadMentor. And the thread yield is implemented in a slightly different way, rather than an explicit thread yield. So basically what you're going to use very frequently will be thread creation, thread termination, thread join. And to simulate a more random execution of a thread program, you could randomly add thread yield in your program. We will talk about it later. Now, we need first to learn how to define a thread. In ThreadMentor, it has a base class named thread. So when you want to define a thread for your own purpose, you simply inherit the public portion or the public section of the base class thread to your derived class. However, to use the thread class, you need to include thread class.h. Frequently, we heard comments from students. My class says the compiler couldn't find a thread class and so on and so forth. It's basically you forgot to include this thread class.h. Now, this is not the system header file. So you should not use less than and greater than, just like what you did for stdio. It's double quote. This is commonly seen mistake. So here, I am going to define a class test, which is a thread, because it inherits everything of the base class thread in the public section. So this is a constructor. I'm sure you can recognize it immediately because its name is the same as the class name, and it does not return anything. And this constructor takes a integer argument. This integer argument is to be used to initialize a private integer here, m. Now, in the private section, you always define a function called threadFunc. Here I show you one argument. You could use multiple arguments. ThreadFunc never return anything, but because threadFunc is not a constructor, then to return nothing, its return type is void. So this is so simple. Now don't forget the semicolon. If you forget it, a compiler will give you so many ridiculous error message. So this is the definition or the specification of the class, thread class test. So then we must write this threadFunc function. Here it is. This is an unfinished version. We will finish it step by step. So look at here. We're going to write the function named threadFunc, which takes one integer argument. Which class does this thread function belong? The test class, and it returns nothing. So this headline tells us that we are going to write a thread function of the class test. Now, here is something odd for modern Java or C++ programmer. As I mentioned, ThreadMentor was designed decades ago. So to initialize this threadFunc, the first line in your threadFunc function has to be thread threadFunc to initialize it. So don't forget this line. Some system could run properly without this line. Some system could not run properly. It's not your fault, of course. It's the implementation's issue because the implementation was done 2 decades ago. So in threadFunc, that is, this function is going to be run as a thread. It iterates 10 times. Every time it prints out the value of n, initialized here, and the value of I, followed by a new line. So if the value of n here is 3, so this threadFunc will print out 10 lines, 0, 3, 0, 3, 1, 3, 2, finally 3, 9. After that, this thread is done. But we cannot do that because we used visualization system. So let me quickly go through it. When you want to design a thread, inherit everything in the public section of the thread base class into your thread class. Then you write your constructor. Most of the time, the constructor of the thread class is giving that thread a name. We will see that. And in the private section, don't forget, in addition to other variables, you always declare a threadFunc there. Even though it shows you only one integer argument, you could use other arguments as well. The thread function returns nothing. Keep this in mind. When a thread is done, it's done. You won't be able to know when a thread is done and waiting for its return value. Because it's when you try to understand whether that thread has done, that thread may have already been gone. So you won't be able to get its return value of your thread. So how do you get the return value from a threadFunc? Remember the thread Remember the shared memory discussion in the process unit. So if a thread function must return something to someone else, the thread function must put the results in a global variable. Because we are writing C function using thread, so that global variable is just a global variable rather than in shared memory. So when you write your thread function, the first line has to be thread. This thread is the name here, double colon, followed by that thread function to initialize it. So in this test class, to be run as a thread, this thread will print out 10 lines. If the initial value of n is 4, then this thread, the test thread, will print out 10 lines. 4, 0, 4, 1, blah, 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 2, 4, 9. So a very commonly used technique in ThreadMentor in the constructor is you give that thread a name. Now, the second thing I want to warn you is, see out is in terms of its printing, it's just like a printf. In the discussion of process, when you have multiple processes printing something to the screen buffer, std out. Results from different processes could mix together. So what did we learn to overcome this problem? We print everything to a string and then use the write system call to write a whole string that is complete line out. And this is what you're going to do in a ThreadMentor program. Or later on, you are able to learn more so that you will continue to use C out. So this is a warning. Otherwise, if you create so many threads, every thread you see out to print something, eventually you will see the same issue you experienced when you use printf in a multi-processes program. Now, there is a method defined in the thread class called delay. Delay is just yield, thread yield. When a thread calls delay, that thread yield the CPU to someone else. So when that thread could get a CPU back, that is depending on the thread scheduler. So sometimes, because all of your program to be written for this courses are simple ones. Simple programs would have simple threads. Each thread may have probably 30 to 50 lines, or at the maximum 100 lines. Most of these lines are printing things, or doing something like initialization or something. So it's very likely a thread will start running to completion very, very fast. It won't give you much feeling of I am running thread in a concurrent way. We will see in the demo of ThreadMentor for a Quicksort demo. So we have to add enough the delay so that the scheduling would be kind of random. So how do we do that delay? Simple. You just generate a random number and call delay random that number of times. Of course, you don't want to call delay, say, 30,000 times. That is ridiculous. You just say you generate a random number and divide that random number by 5 so that the number would be 0, 1, 2, 3, 4. Then you write a loop, say j from 0 to 4. Then in the loop body, you just call delay. In that one, you actually simulate more realistic scenario when you run your threaded program, because all of your program to be discussed or to be written are pretty easy. So as I mentioned to you, the code here for thread func is incomplete. We need to add more there. So what we have done on the previous slide is just we defined a thread class and we put something into the thread func to be run as the actual code for that thread. But after creating that thread will not run. That thread will not run. To run that thread, you have to call the begin method, uppercase. You have to call the begin method to start running of that thread. So let's complete the main program so far. So here, remember, the class we defined was test. Here, run is an array of 3 elements. Each element is a pointer to the class type called a test. And then we have a loop. The value of I goes from 0 to 2. That is, this for loop would iterate 3 times. Every time, every iteration, we knew a test class and supply the value of I to the test class as the initial value of n in the test class. So after the creation of this test class, a pointer will be returned, which in turn will be saved in run I. So run I is a pointer to the created test class I. And that class variable n in the private section is initialized by the value of I. So run 0 is a pointer to test class 0, whose variable n is initialized to 0. So in that class, when it runs, it will print out 0, 0, 0, 1, 0, 2 to 0, 9. So the next time when we execute this stream again, test will be initialized by the value of 1. So run 1 is a pointer to the test class. That will be initialized by 1. So the value of n would be 1. So when that thread runs, it will print out 1, 0, 1, 1, 1, 2 to 1, 9. Okay? So after creating this thread, we have to call the begin method of that thread in order to start executing that thread. Keep this in mind because we use pointer. So we use reference to call the begin method. You should not use the dot notation because we created and the created class is returned as a pointer. So in this way, the main program creates the first class, run it, and goes back for the second iteration, creates the second thread, runs it, and then create the third class and runs it. So after creating all 3 and running all 3, we are here. The main program has to do many things. So my question is, up to here, how many threads are running in the system? Please pause and think about this question. How many threads are running? Please pause. Now, if you want to say 3, because create 1, runs 1, create 1, run 1, so we create 3. That is almost right. But do you remember even though this system could be a user level thread system, the main program itself runs as a process which is also a thread. So don't forget, the main program itself, when it runs, is also a thread. So here we have actually 4 threads running, and here we have 1 thread running. When I is 0, we have 2. When I is 1, we have 3. When I is 2, we have 4. So when we reach here, we have 4 threads running, 3 created by the main program, which is also a thread. So far, I hope you understand it easily. So here are some notes. Before calling method begin, you have to create that thread. Before you call begin, even though you have created that thread, it does not run. To run it, you have to call begin. The second one tells you that threadfunc never returns. When threadfunc reaches the end or executes a return, it disappears from the system. So you have no way to predict when it returns in order to get the return value. So when the main program finishes execution, never ever call the exit system call. Because when you call the exit system call, it means the main program exits. When the main program exits, everything created and owned by the main program or the process running the main program will be gone, including all the running threads. So do not use the system call exit. How do we overcome this problem? In addition to the begin methods, the thread class actually provides you another method, exit, with uppercase E. So do not use the system call lowercase exit to terminate the whole program, because it terminates everything of that process. So here, this is a complete version of the threadfunc. This is the header of the threadfunc function. This line is required. And then we have an integer iterate 10 times. Every time we print out the value of n, followed by the value of I, followed by end of line. And finally, this thread terminates. The thread calls uppercase exit to terminate itself. So this is a very commonly seen mistake. You may want to say, oh, I'm done, but I get nothing in output. That's only one reason for you to use uppercase exit here. The second reason you use this uppercase exit is this uppercase exit and the begin method actually informs the visualization that something has happened. When you call the begin method, the begin method informs the visualization system, saying that a particular thread has started running. Please take care of this thread's activity in all subsequent calls. Then, when you call the uppercase exit, this exit simply informs the visualization that the thread is about to exit. This thread will no longer sending you any further message, so you could ignore it. So the begin method informs the visualization system saying that some new thread started. The exit, uppercase exit method tells the visualization system that this particular thread is gone. Ignore it because it will no more sending you any messages. Let me warn you again. If you use cout in your programming number 3, you could get mixed output on the same line from different threads. So before you learn anything further, make sure you use sprintf followed by write. So we are almost done, except for one thing. Remember, when we talk about multi-processes under Unix, the parent must wait the child to complete. If the parent ends before the child terminates, the child will become an orphan. Whatever the parent asks the child to do will become nothing because the parent will not get that result back. By the same reason, in threads, the concept is referred to as thread join. You may want to ask, why don't we use wait? Well, if you use the system called wait, this thread would wait depending on the system you are using. The system may interpret your thread wait to be a process waiting for its child, for one of the child's process to complete. Or if you involve some synchronization steps, that wait could be a semaphore wait. So the universal language for a thread to wait until one of its child thread to complete is referred to as thread join. So a parent thread creates so many child thread to run. Each of the child threads could produce some results and save the results to some global variable for the parent thread to pick up later. So how does this parent thread knows their child thread completes? So that the parent could pick up the results computed by that particular thread. So you have to call the join method of that child thread. So the second clause simply tells you the parent must wait until all of the child threads complete. Otherwise, when the parent exits, all of your child thread exit as well. This is very important. So as we mentioned, we use the join method for a thread to join with that thread. So suppose thread A must wait for thread B to completion. Of course, in this case, B is a child thread of A. So in A thread fun, A used this way to call the join method of B. If B is created through pointer, or you use this dot method to call B, if B is not created by pointer. Now, let me remind you. If you want to wait for a child thread of U to complete, you call the child thread's join method. It's not the other way around. So thread join is very similar to process wait. Suppose thread A waits to join with B. We have two possibilities. If A reaches the join call before B exits, that is when A calls B's join, B is still running. Then A waits until B completes. If B exits before A can reach the join call, then A continues as if there's no join. An example I used to illustrate this join, these two bullets for join for probably more than 2 decades goes as follows. Suppose you and your brother living together. Now you are preparing for the final for this course. But it's dinner time. You feel hungry. And say Domino Pizza Hut would not deliver to your location. I'm not sure whether there is a location they don't want to deliver around Holton. But let's assume that the pizza delivery refused to deliver pizza to you. So what would you do? You think about it, okay, your brother is in the house, so you do not have to run out and get the pizza. So you simply give your brother $20. Ask your brother, please run out, get a pizza and some snack or some salad or some drink for me, please. So you are the A. Your brother who is going to get the pizza for you is B. Then after issue this creating a child thread, asking your brother, creating your brother is the child thread and ask them and run. Then you return to your study for the final. So there are two possibilities. After you finish the study for the final, and you are A, but B, your brother, is nowhere to be found around the house. So you have to wait until your brother comes back. Or your brother has brought the bag, the pizza and drink, and leave it on the kitchen table. So that is your brother finishes his work. So when you finish your study and course join, because your brother has exited, you simply go to the kitchen table, grab a piece of pizza, maybe sharing with your brother. So this is the meaning of thread join. So we're almost done for this extremely simple example. Now let's go through the thread class again. This class is referred to as test, and we have a constructor which takes a integer input to be used to initialize the private variable n. And we have thread func, and this is the definition of the thread func. This is the first line. Always remember, when a thread exit, never just execute a return or even without a return. The last statement to be executed in a thread has to be exit, the uppercase exit. Now let's look at the main program. The main program creates the first thread, runs it, creates the second thread, runs it, and creates a third thread and runs it. So up to here, all three child threads are running. But this main program cannot exit. If the main program exit, all three child threads will be gone. So you probably won't get a complete output from all three child processes. Therefore, just like what you have done for program 1, program 2, when you use multiple processes, you just wait or all three are done. So here, we wait for run 0 thread to complete. When run 0 complete, well, we don't know whether run 0 has completed or not. But anyway, if run 0 has completed, this join call serves no purpose. You just go back for the next I. Now, if run 1 is still running when the main program calls join, so the main program will be blocked. So in this way, if we finish the second for loop, we are sure all 3 child threads have completed the job. So the main program calls exit, uppercase exit, to indicate to the visualization system that the main program has done, so that the visualization system could clean up everything, pack up, and terminates. So this is a very, very simple program. Now, let's use the same idea to write a quicksort program. Remember, you probably learn quicksort in a recursive way. So in each recursion, the quicksort program takes an array section in. L is the lower bound, U means the upper bound. So for each recursion, the quicksort program takes an argument, meaning sorting the array A from L to U. Then in the quicksort program, you use whatever method to find a pivot element M. After pivot element M is found, the left section to the pivot element, that is L to M minus 1, all elements are there are less than the pivot elements. And all elements to the right of pivot element, that is from M plus 1 to U, all of these elements are larger than pivot elements. What does that mean? It means the pivot elements is already at this correct location. So then we recursively call quicksort by giving it the left section. After left section is done, then from the left section to the pivot elements, this section is sorted. Then recursively call the quicksort function to sort the M plus 1 to U. When both subsections are sorted, the array from L to U are sorted. So this is what the recursive quicksort does in order to sort it in an array. Let's ignore its complexity because we only need the idea. Now think about this. In a recursive quicksort, after finding the pivot elements, we recursively call quicksort to do this part. After this part is sorted, we recursively call quicksort to do this part. So sorting this part and then this part are independent of each other, which means M is already in the final position. When you permute the elements here, it doesn't matter because all elements here are less than the pivot elements, and all elements here are greater than the elements here. So while you are sorting this section, it won't affect this section. This means sorting this section and this section are independent. Now, remember in the thread discussion, if this data are independent, why don't we create 2 threads, one to solve this section, the other to solve this section? Then instantly, we have a concurrent version of quicksort. So this is what we have said. A recursive quicksort receives lower bound to upper bound. The partition procedure, I'm not sure whether you learn the partition procedure or not. Some data structure book would provide you with a very elegant partition procedure rather than the original partition procedure offered by Tony Hoare, the one who invented Quicksort. Anyway, when you get their pivot elements, sorting L to M minus 1 and sorting M plus 1 to U are two independent tasks. So we could create first thread to sort this far. After creating the thread and running it, we could immediately create the second thread and running it to sort the right section. So this thread and this thread are run concurrently. So this is the idea. So our strategy goes as follows. A thread, when you create it, it receives an array section, A, in lower bound and upper bound. So in other words, your thread func receive lower bound, upper bound, and the array address A. And then in thread func, it calls the partition procedure to find the pivot elements. Once the pivot element is found, this thread func create a child thread, giving it A, L, and M minus 1. Immediately runs it. Then this thread func create a second child thread, giving it A, M plus 1, and R. After creation, runs it. So far, we have two concurrently running child threads. After that, this thread func issues two thread join, waiting for these two, this child thread and this child to complete. Then this thread func is done because this thread func has successfully sorted array A's section from lower bound to upper bound. So this is our thought in order to create a concurrently running Quicksort program. Now let's write a program. Quicksort.h. Always remember, it's good for you to separate your policy and a mechanism as we discussed in the first lecture of this unit. So the specification part is the policy, which is the .h. So we're going to define a class called Quicksort, which inherits everything in the public section of the thread class. And this Quicksort class has a constructor, which takes the lower bound, the upper bound, and an array. So in the private section of this Quicksort, we have a lower bound and upper bound and a pointer to that array. And finally, we have a thread func. Nothing else. For this thread, it's nothing else. It's this simple. Then let's do the implementation part. The implementation part is in the .cpp. Now, because of space limitation, when you write this implementation, you should include your quicksorter.h. Don't forget it. I'm sure you will remember it because all of you are good programmers. So let's do the constructors. The constructor receives lower bound, upper bound, and the address to the array A to be sorted. Remember this colon. Each of this pair means we use the argument to initialize the variable low. And we use the argument U to initialize the upper bound, declared as private variables. And we use this pointer to the uppercase A array passed to it to initialize the local pointer. We try to remember. And then don't forget to give this thread a name. How will you be able to give thread a name? You just assign a pointer to a string to it. How will you be able to generate a string? We talk about several mechanisms. You could use a string copy, a string concatenation, and even string f to generate a sequence of numbers and put them together to create a new string and save the new string name to thread name. Why you need to thread name? Simple. When you run your program, multi-thread program, the visualization, if you do not provide a thread name for each thread, when the visualization window shows up, you don't know which component is for which thread. And if you do provide a thread name for each thread, so the information of that thread would be marked with a label. And that label is exactly the thread name you provide here. Okay, then let's look at the thread func of the Quicksort class. This is a typo. I hate Microsoft. Every time they simply capitalize the first word. I know you know it. So this is the first line required. Now, in this thread func, we need to create two child threads, which is also of the type Quicksort. So because we're going to create it by pointer, by using pointers, so we define two variables, left and the right. Left is a pointer to a Quicksort class. Right is also a pointer to a Quicksort class. Then we declare M to put the position of the pivot elements. Then we call the partition function to find the position of the pivot elements and put it into M. Now we have everything. The remaining is very simple. We create a Quicksort thread to sort the left one, going from lower bound to n-1, providing it with the array name. After creating this thread, C++ would return you a pointer to this newly created thread. And you this assignment save it to left here. And then we run the begin method of the left thread immediately. So right after running this thread, of course will take some time to complete. Then we create the second thread, giving it the right section from n+1 to the upper bound. And this creation, this new, would return a pointer to the newly created threads, and then runs it again. Now we have created one left thread, one right thread. Don't exit. If you exit now, both threads will stop running. So we have to wait for the left thread to finish and wait for the right thread to finish. Now, after both threads are done, call the exit function to terminate this thread func. Remember, this is uppercase. So isn't it quite simple to do? Now, finally, this is the main program. In the main program, we need to create the first Quicksort thread. Just like in your main program, after reading a whole array, you call Quicksort, recursive Quicksort function the first time. It's exactly the same thing. So because we need to create a Quicksort, so we declare a pointer to Quicksort. And then we have an array, lower bound, upper bound, and the number of elements. So let's say we read the integers into A, assuming that the number of integers read in is no more than maximum size. So the lower bound initially is called 0. The upper bound is n-1. So that we create a Quicksort thread, asking it to sort the left bound lower bound 0 to upper bound n minus 1, and a pointer to it. So the new statement would return a pointer to the threads here. After the thread is created, run it, followed by joining it. Then we exit. So this is very simple program for you to understand. Now, some of you may want to say, I really do not want to pass the array pointer around. That's fine. In that case, you just move this array outside of every function right after the inclusion of the header file IO stream and namespace, and declare INTA outside there. Of course, you have to supply this value. So in this way, you could remove all of these third argument. So please review these several slides and make sure you understand the whole thing. I'm sure it just take a 1 or 2 minutes for you to understand the whole thing before continue. Because next, we're going to talk about some technical thing for you to compile this program under ThreadMentor. So please pause. Okay, before continue, let me ask you a question. Don't read this part. Now, look at this one. Still the same. Create a thread, run it, and wait for its completion. Then create the right one, run it, wait for its completion. Is this a correct program? The answer is yes. This program definitely delivers correct results. But is it a good program for concurrency? Think about this before continue. Okay. In my experience, most students would answer my question correctly. That is, there's no concurrency in this program at all. See, for this, to sort this section from lower bound to upper bound, you create the left thread and you run it, that you wait for the completion. So the left thread is gone, then you create the right thread, run it, and wait for its completion. So isn't it very similar to the recursive version? So this is not a good solution at all, although it is a correct one because it does successfully and correctly sort the input array. But in terms of concurrency, it is a wrong one because it does not fulfill maximum concurrency. So in all subsequent programs, you must make sure when you can make the program to run concurrently, you just do it. Don't make a concurrent concept to become sequential like this. This is a commonly seen mistake in this class. Then let's see how to compile with ThreadMentor. ThreadMentor allows you to see the visualization so that you are able to visualize what's going on in your program. So all the needed components in order to initialize the visualization have been added to the thread class library implicitly. So you don't have to do anything about it. You just run your program as if, just like the previously shown Quicksort, you just write a program that way, you run it, then you have the visualization for free. But you could also run your program without visualization. What does that mean? It means you have to compile your program properly so that a correct library will be used. There are two versions of ThreadMentor libraries. One with the visual, the other is non-visual. The visual library, when your program runs, it simply brings up the visualization process and shows you all activities related to synchronization and thread management. That is basically for you to understand what went wrong in your program. Because you wrote the program, you know every bit about it. Your logic may be wrong, or your logic may be wrong, but you run it several times, you don't see the bugs. But the next time, the bugs appear. So from seeing everything that is happening in your program would actually provide you with a much better debugging aid than bring up a debugger. Because once you bring up a debugger, you change the behavior of your executing program. So the use of visualization system under ThreadMentor, yes, the visualization system also changes the behavior of your program. That's true, but the impact will be minimal. So when you feel that your program is correct, everything is fine, then you could recompile your program without the use of the visualization system. That is, you compile your program with non-visual system for submission. The grader would not want to see the visualization because it would waste his time or her time. So how to compile your ThreadMentor is just a makefile. This makefile is available in the common directory. You simply make a copy and modify it. The next few slides simply teach you how to modify or how to use this makefile. This makefile must be presented with 2 slides. So you probably don't need to change everything if you run your program on this CS machine, say Whopper. So let me explain to you. To the left-hand side of the equal is the name to be defined. So CC defines the compiler, C++. And this flag, use this only when you work on your home machine. I'm sure many of you have Linux machine on your laptop or desktop. So if you run ThreadMentor there, you may want to add this flag. When you submit your program for grading, remove this line. Okay. Then the next one is C flags. These flags are for compilation. You don't need to change anything. Always remember when you submit your program, remove this flag. So this C flag, we have something here. These 2 flags is -W uppercase. These 2 flags eliminate the most common warning message related to ThreadMentor. Remember, ThreadMentor's the system, the visualization system are compiled with older version of C++ compiler. Under the new version of C++ compiler, you will see a whole lot of warning messages. So those warning messages are very annoying. So at this line, these 2 flags would help you to remove most of the common warning messages related to ThreadMentor. And you may want to add this flag. This flag would eliminate all warning messages. Is that a good practice? No. Sometimes most of those warning messages related to your program, if you use this flag, would also be removed. So you don't know what could be wrong in your program. So if you don't want to see all the warning message, you don't need to add this one. But when you submit, add this one back. So in other words, for the C flag lies, everything has to be there. The D flags shows you where to find ThreadMentor package. I use ... here because that is a very long path. So never modify this line unless you install ThreadMentor on your local system. Now, I flag indicates where to find ThreadMentor's header file. It's local, EIT, Linux, and blah, blah, blah. Don't change the slide when you submit your program. And tmlib, or that is TM library, this library shows you the visual library. This is the path. And tmlib underbar NV, and NV means no vision, is this line. So if you wish to install ThreadMentor on your local system, local Linux system, we will talk about it a few slides later, you feel free to copy that Linux 64-bit version to your system. Then what you need to change is this line, because when you install, this path is definitely different. This path would also be different. This path would also be different. The D flags would also be very different. So refer to this makefile as a reference for you to change this makefile on your local system. But don't forget, when you submit your program for the grader to grade your program, these lines has to be restored. So I strongly suggest you, when you make a copy of this makefile, name it as makefile original. And then you copy this makefile original to a different location, saying something like that, makefile my own use, something like that. So what you need is, remember, you could add this line to your local makefile or makefile local and remove it in your submission. And this line has to be completely there for your submission. And if you don't want to see many error warning message on your local system, remove it for your local makefile and change these 4 paths for your local system. So these are all you need to know. Then let's see some other defined name. The first name is object file. It tells the maker program how to generate object files. That's what kind of object files will be generated. That is, here we have quicksort.o, which is the compilation results of quicksort.cpp. And this .o file, quicksort-main.o, is the result of compilation from quicksort-main.cpp. And this exact file indicates the executable binary executable file name, quicksort. So object file, this line indicates the file name, the object file name. This line tells you the executable file name. Then let's see how to compile. So I'm sure you know how to use makefile. Makefile usually consists of two lines. The first line has a colon here, telling you how to generate this thing from this thing. In other words, on this first line, we try to tell the make program to generate executable file, which was defined as Quicksort on the previous slide, from these object files, which is quicksort.o and quicksort-main.o. Remember that? So this slide tells the make program use these object files to generate this executable file. The second line is the command line to generate this thing from this thing. So when you write the second line, the first character is a tab. Don't put a space there. So here, this is the compiler name, C++. We have flags here. Now, this is for you to use in your local machine. When you submit, remove this flag. Then -o means the output file. The output file is this name, Quicksort, and the object file is quicksort.o, quicksort-main.o, and the tmlib. And this is, we are going to use the pthread library for ThreadMentor thread support. So this line, if we put all the stuff into this parentheses, it means C++ -o, quicksort, quicksort.o, quicksort-main.o, tmlib, and this string. Do you understand this? Then, because we need this .o file in order to generate the executable, so each .o file has their corresponding command in order to create it. So this slide shows that quicksort.o is created from quicksort.cpp. Look at this column. We compiled it. We compiled quicksort.cpp with D flags, I flag, C flag, and this is a compilation only due to that C. Compile what? Compile this quicksort.cpp program. The result will be quicksort.o. Then we compile, in order to get quicksort-main.o, where is the source file? Is quicksort-main.cpp. To compile C++ compiler, D flag, I flag, C flag, -c, meaning compilation only, followed by the source file. Then we have something defined here, no visual, colon, followed by all the object file. And then compile it, flag. Remember here, remove this one. When you submit your program, -o, the executable file, object file, tmlib-nv, meaning compile the whole thing without visualization. And then clean, remove these files. So when you submit your program, what you need to do is you write different program. You have your .cpp, change it, and you have your own generate.o and so on. Just replace the source file name and the object file name accordingly. So I don't think this make file would make much trouble for you. The only trouble in the past semesters were you fail to submit the correct makefile for compilation if you run your program at home. So as I mentioned earlier, you copy the makefile from the common directory to your machine. name it as makefile-original. When you want to use when you create your own file, you make a makefile, call it makefile local. Okay, so when you submit your program, modify makefile original by removing all the needed stuff, replacing the file name, and so on. Then submit makefile original. Don't forget to remove original because the grader only recognizes makefile. So by default, as shown here, you will see your ThreadMentor program is always compiled with ThreadMentor visualization. Now, after using ThreadMentor visualization, if you are comfortable with it, you could recompile your program without visualization with this option. And after several times, you may have so many .o file there, so you could use this option to remove those unneeded files. So let's see how, with this makefile, how do we compile? So the following, you just type make from the local directory, the same as the Quicksort file. So when you type quick, it would compile your .cpp file to .o and link those .o together with ThreadMentor visualization library. Now, what if you don't want a visualization? You simply type no visual. Here, V is uppercase. Now, after testing for so many times, you may have so many versions of .o files, so you just make clean to remove all the .o and executable files. So this is very easy. So if you are not very used to makefile, the Concurrent Computing course webpage has a link providing you with all the simple facts about the use of make in the makefile. I try to be rather slow so that you could pick up the first time listening. If you fail to pick up everything or you missed something, don't hesitate to rewind and watch second time. Now, before you can actually run your ThreadMentor program, you have to modify your shell resource file. Here is an example for the C shell resource. It starts with a dot. This file should be in your home directory. You won't see this file if you just type ls. You have to type ls followed by -a to list this hidden file. Then edit this file. Edit this file to add a search path for visualization to this resource file. Depending on the shell you are using, the name of this shell resource file could be different. And the way of set search path may also be different. So here is an example based on the C shell. So set path, this PATH is referred to as an environment variable. This environment variable usually has all the needed files for you to search for the executable files. So in C shell, this is a new path, the equal sign followed by a pair of parentheses. This $sign path is the existing path name. Now, what you want to add is the path name leading to the ThreadMentor binary folder. This binary folder would have all the executables for ThreadMentor, in particular, the visualization system. So this line simply means add this search, this path to the existing path name, path environment variable to create a new one. Okay, let me repeat. This is an example for the C shell resource. Your shell may not be C shell. You have to find out what kind of shell you are using or what the resource file is. So use ls followed by dash lowercase a to find this hidden file. So you, in your home directory, you will always find such a file, because when you open a terminal, as we mentioned several times, that terminal would be controlled by the default shell. That default shell would find the search path. So the next time when you type some program name, it will start searching all of the search paths here in order to find it. So this is an example for C shell. If you are not using C shell, the syntax may be slightly different, but mostly they look very similar. So path is an environment variable. We need to include the binary executables of ThreadMentor to the search path. So put the path environment variable name to the left of equal sign. To the right side is a pair of parentheses. The first one is $sign path. That is the current search path. It may not be one, it could be several, depending on how you set up your environment variable. Then you add this search path for ThreadMentor there. Then you exit your editor. But there is a warning. Right after you save it, it does not mean the shell knows your new path, because your old path has already been loaded into the shell when the shell is started. So what would you do? Simple, log out and then log in again. Will you log in the next time? When you log in the next time, the shell, the default shell, would load the newly created path in. Okay, even though you are doing it with multiple windows, I strongly encourage you to log out from your account and then re-log into your account so that the newly set up path will become effective. There are many ThreadMentor examples available at the ThreadMentor tutorial site. As I mentioned earlier, the development of ThreadMentor was supported by National Science Foundation. And this site was created probably more than 20 years ago, when C++ was in its older version. So when you download this example program and compile it, you'll find at least two annoying things. 20 years ago, when we include IO stream, we did a .h. That is, all example programs available here would include IO stream.h. So what you need to do when you copy this file to your local machine, remove that .h. And then the second one is remember to turn off most of those ThreadMentor related warning message. We saw the makefile earlier. And I am sure when this program were copied to this site, due to some editing issue, there could be some syntactical error. I'm sure you will be able to find it. And if you found some, please let me know. I will appreciate very much. It's so unfortunate that I don't have time to make all change of these programs. And finally, due to COVID-19, most of you may not work in the CS lab. So the next question is, what should I do if I work at home? That depends on which system you use. Some of you, in my experience, even though before COVID-19, some people has already had local Linux machine, desktop or laptop at home. That's the easiest one. You just make a copy of ThreadMentor 64 bits from the common directory to your local system. Depending how you install it, modify the search path, inclusion path, and so on, you are all set. Some people may use a dual boot system, Windows, Linux, or Windows Mac OS. But anyway, let me provide you with a flowchart. If you are using a Windows-only machine, Windows, of course, cannot run Linux program. So you need to install two programs, PuTTY. PuTTY is just a SSH application for you to log into a CS machine. But PuTTY alone does not support graphics. Our lab machine use the X window and other graphic capability like what we are using for ThreadMentor. So if you use PuTTY, you won't be able to see all the visualization stuff. So you need a second application called Xmin. Install these two on your Windows machine. Then you could use PuTTY to log into your CS account. Use some editor there to create your program and run it even with visualization. So this way, your submission is pretty easy. On the other hand, when your program runs on the CS machine, generate a visualization. Visualization would send you back the visuals to your local terminal PuTTY window. That's going to be quite slow. So whether you want to do it is your choice. For the first two programming assignment, it's fine because we don't use graphics. But from program number 3, you will start using graphics. Then you really need Xmin. So this is the easiest one to do. The second one is you install the VMware Workstation. VMware Workstation is for Windows, which is free for you to download from the university software download page. Then you have a virtual machine. You can install the Red Hat Linux, which is exactly the same as the system being used in CS Lab. Under this virtual machine, you have a Linux, and then you install ThreadMentor under this Linux. Then you could do your work locally. You have all the graphics capability and so on. After you are all done, modify your make file so that all paths will lead to the correct place. You move your files to your CS account, and then always test your program there before submission. Why will be clear later. So if you are using a Mac OS laptop or desktop, I'm not sure how many of you would use the Mac Pro. It's too expensive, but I feel quite comfortable in using a Intel version of Mac Mini. So for Mac, you install the VMware Fusion. Look at it, it's different. For Windows, you use VMware Workstation. For Mac, you use VMware Fusion. Both are available from the university download page. Then install Red Hat Linux on this VM, so the remaining will be the same as Windows. After installing your Linux, you could install ThreadMentor, do your work locally, and move all your files to your CS account with modification, and then always test your program there. Now, if you use a native Linux machine, you simply install ThreadMentor. It's all done. So see the links under the programming information section of the course information page. It tells how to submit, how to install Putty, and how to set up Xmin, and how to find VMware Workstation and VMware Fusion, so on and so forth. So notice here, this path is not applicable to Apple Silicon M1 CPU computers. I'm aware of that. Parallel is testing a version of their virtual machine for the M1 chip. VMware talk about a possible new version, and I hope they will release the new version early, but there's no guarantee. So if you use a M1 chip computer, you probably have to use SSH, log into a CS machine and enable X forwarding in order to get graphics back. Now, lastly, why I asked to test your program before submission, again, is due to the dynamic behavior of a multi-threaded program. When you have a virtual machine, on top you have a Linux, it's very likely you don't have many processes or threads there. So definitely, when you run ThreadMentor there, your Linux system is a lightly loaded system. For a lightly loaded system, the thread you created under ThreadMentor could run more frequently than when it runs on a heavily loaded system. But when the grader is going to grade your program, he or she may use a CS machine, say Colossus, Whopper, and several available machines. So there will be so many processes running. So the CPU scheduling has to be different when you run ThreadMentor on your lightly loaded machine. So that means when you run your program on a heavily loaded machine, the program behavior could change due to these external factors. For an example, memory available and CPU availability and so on and so forth. So this is why right after you get everything done here, test your program several times. Whether you're going to use visualization doesn't matter. because the grader would use no visual to test your program. So you could just compile your program without visual and run it. Because it's all text output, you could get your program output back fairly easily. So don't forget to test your program on a CS machine, because most CS machines like Whopper, Colossus are servers. They serve more processes than your local Linux running on a virtual machine. So your program behavior could change due to whole lot of external factor. So this is the way I recommend you to do your homework at home, your programming assignment at home from programming number 3, 4, 5, and 6. And always test your program before submission. So I think this is the slide for lecture 2. Lecture 3 is a very short demo of running ThreadMentor. Actually, we just use the Quicksort program as a demo program so that you will see what kind of a visualization components would be available. This is, of course, the very beginning. In some later lectures, you will learn more about it. So let me stop there, and good luck. Goodbye.